All right, so welcome to the second part of the x86 assembly. So today we continue on from Tuesday and hopefully expand into what can you do in assembly. But before we go there, while the TA are grading your exam, right? We actually caught student cheating in the midterm. So define cheating. It can be you are copying someone else, you are copying from somewhere without telling us, you are posting the questions somewhere trying to get the answer. I left enough trail in my question so that I know it's actually our exam. All right. So if you did that, uh, you're gonna get penalized for sure, right? So like let me say this first. The exam is designed to test you, not testing someone else on how to solve these questions, right? And if you seriously think that you can just cheat through all your exams until you graduate, and then you get a decent job in computer science company, right? Yeah, I don't think so, right? They'll know that you can't program, and once they know they cannot program, we'll find another job, right? So that's not good, especially this early in your university career. Like you want to make sure you have the foundation that you can use for the next class. And if you cheat on the first like an early class like this, you're gonna have no foundation at all, and your whatever you try to build will collapse, right? So don't do that. It's unacceptable. So I'm gonna apply our policy. But here's my option for you. So if you cheated, you have two options here. You can DM me on Discord right after this class until the end of today. Until the end of today. That's actually why I'm waiting for the rest of you guys to show up in our class, right? Because I want to get this message across. If you cheat on the exam and you DM me on Discord saying, "Hey, Ajahn, I'm sorry, I cheated on the exam on this part and that part," you admit the fault, you get 0 for your midterm. If not, we'll apply a standard policy that I have, which is I'm gonna apply negative 100% on your midterm, which will fail you because we know already who cheated. All right. So if you admit your fault, and well, obviously this is the first instance of cheating for this class, you get 0 for the midterm. Well, your grade will be impacted, but you can pass the class. If you choose not to DM me, by default, if I apply this grade, you fail, right? How will I know if it, wait, what? Oh, so if you did not talk to anyone or didn't ask anyone else, don't DM me anything. You're safe, all right? This, think about it this way. We detected to the point that it's clear that who did what, all right? So if you did not talk to anyone, you did not ask anyone else, it's fine. And before I apply, yeah, if that's your case, don't worry, you'll be fine. I just want to make sure that I get the point across for those who cheated, right? Online exam, I know it's like that's a lot of things that would go through your brain while you're doing the exam, just so that you can get better grades, right? I think we need to teach honesty, and I'll give you an example, right? In the US, if there's an online exam like this, the professor would basically trust the students and will catch cheaters, right? And will fail them. But we should be able to trust your work that it comes from you, right? And I think this is the basis of how you would run a society, right? You have to be honest with what you did and what you did not do, right? Um, that would make our society, to be honest, like Thailand, for example, less chaotic, right? There's less people cheating. Seriously, your life would be better. It's just as simple as that. You have people who know how to do the job in the job. You have people who didn't cheat through like let's say for example, right? If you have friends in the medical school, right? Say go to Chulalongkorn or Mahidol University, right? In the med school. Would you like to get treated by a friend who cheated? or a friend who never cheat through any classes, just answer me with that question. Which one do you prefer? Which doctor do you prefer? The one who never cheated and the one who cheated through all their exams, right? It's just as simple as that. Programmers are the same. So, okay, I hope that the point gets across, right? And for those of you who did not cheat, I appreciate it, right? Um, it's I know that because online format, it's like there's just so many things that will go through your mind. Asking if my friend finished the exam count as cheating? No, no, that doesn't count as cheating. All right, you can ask your friends if you finished the exam or not. Definitely sure. I'm not evil, guys. I just give me a second. Sorry. All right. So sorry. It's like so many commercial calls these days. Yeah, asking if your friend finished the exam also does not count as cheating. Uh, Asking your friends how did they do on the exam does not count as cheating. What gets counted as cheating? Asking the exam questions somewhere on the internet, that counts as cheating. Um, Copying your friend's code, that counts as cheating. Copying your friend's solution, yeah. But I mean, so I know that this can happen. So I put enough trail on my own question so that I know it's definitely my question. You notice some set like some configuration in my questions are kind of odd. So yeah, someone posted a question on the internet, and yeah, I know it's my question. There are ways I can ID that that's my question. All right. For example, right? If I say integer three, who would use a 3 byte integer? Seriously, like that exact number with the exact question. Or if I look at the code, it's not building up from our sample code, but it's obviously found on the internet, for example, right? So those things are like we gotta talk, right? So if I found those things, right? So hopefully it's more clear for those of you who tried your best, because the exam again is to test you, and I really appreciate when you try your best, right? It's not fair for your friends who actually try, right? Cheating is never fair. By definition, it's not fair, right? And my job is to make the exam fair to everyone. So if you cheated, you get the lowest grade possible. All right. So let's move on. Let's move on. So let's move on to the less serious discussion. We are on this slide for 10 minutes already. All right. Any other questions about like does this count as cheating? I mean, you know what you did, to be honest. If you don't have the ill intention, that's okay. I'm not evil, right? But I want to know that I want to make sure that people don't just pass the class and think these are okay. All right. So let's continue on with the topic we should learn on the class, right? So we talk about register, we talk about memory. So I want to kind of like show the difference a little bit. Here's the kind of visualization, right? Oops, sorry. So the questions are topic, but in the poll for the makeup class, is the day wrong? Oh, okay. Don't look at the date. Look at the day of the week. Look at the day of the week. So if it's Sunday, then it's Sunday on some week. I just want to know what day of the week works best for everyone. But yeah, thanks for spotting that. So I can tell you. Basically, it's I cannot get the date, the number out of the poll. It just there's no option for me to do that. So I would just look at Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, and Saturday, and that's all. Like I just want to see what day of the week worked for everyone. All right. So is it more clear? All right. So now let's look at yeah. So just look at the day only. It's like Sunday I'm free, or Monday I'm free on like this slot between noon to 2 o'clock. Just put in, just click on those, and it would like make it green, and so I know that you're free. Yeah. So over here, register are things in the box, right? Program counter, register, right? Some processor would also have the special register to store the address that you want to access for the data, right? So these are really, really fast unit that you can reach out and look at the value. Then you have the I/O, right? That I just draw, input and output that come from the red boxes. These are extremely slow, and they interface through the memory. And then you have the memory, which is the green box, right? And the dash arrow here is the control, right? That the CPU. Basically, everything in blue here is a part of the CPU, including the memory address and memory data register, right? Those are inside the CPU, and it control everything else, right? Think of it as like a mastermind that control everything, and it would allow you to interact and move the data around and process the data. So let's expand into the register in the x86-64. So these are your Intel and AMD CPU. So these are kind of like the default CPU that you get, right, when you buy a laptop or desktop. So you might have seen this part already, like RAX, RDX, right? These are the name for the register. Because I said register are like temp variable, right? It's like when you have temp1, temp2, temp3, temp4. This is the same. So whenever you want to use temp1, you type in %RAX. So that's the variable name, right? And RAX comes in 4 different variation. The one that would take in all the 8 bytes, the one that only take in the first 4 bytes, the one that would only show the first 2 bytes, and the one that takes only the last byte. So what does that really mean? So let's say this is RAX, right? %RAX. You get all the 8 bytes in it when you want to read RAX. If I just say %EAX, it would only take this part and return it for you. If I say %AX, you only get the first 2 bytes, and if I say %AL, you get the last byte only. And the data basically is the same piece of data inside the register, right? Any questions about this? So how many of you have a question about why does it suddenly stop at RBP and then it changed from R8, R9, R10, and R11 up to R15? How many of you will question that? Like why stop and just change it to a number? So there was a historical reason for that, but let me ask you, which one is simpler? Should we just go with R0, R1, R2, R3, R4, R5? Is that simpler, basically? Why use the letter again, right? That's actually that's a really, really, really old reason for that. We don't have that reasoning anymore. So if you look at many modern ISA, you see that it starts from 0, like V0, V1, V2, V3, like something like those, and it's fine, right? x86 back in the day, when we don't have the 64-bit chip, like back in the day when Intel just formed a company, right? There's a name tied to this register. RAX, people used to use it to accumulate data. RBX, people used to use it as a base for something like base plus a number. We use RBX usually for a base plus a number. RCX would be used like a counter, count up and down. And RDX is used to store data, so it's called RDX. Then the source and destination index, these are basically for an address, usually back in the day. That's why we call source index and destination index. A source in the memory, a destination somewhere in the memory that you want to store the data to, right? SP and BP are the stack pointer and the base pointer. These are used mostly in function calls. And that's why it's named that way. And then people realize it's kind of pointless because we can use any of these registers for other reason too, right? So the next set of registers like R8, R9, R10. So hopefully it cleared things up a little bit. Now you might be then asking, why can't I change RAX to R0? So how many people have that question in mind then? Like, then why can't I change RAX to R0? How many people feel weird? Why don't Intel change RAX to R0 then? If I said there's no really point into using RAX. Actually, it cannot be changed if there's a big if there. So if you have an old program, yes, backward compatibility, thank you, that's the reason. So if I have an old program that write assembly, like I write a program in assembly code, right? And then I use RAX. I need to keep using and supporting RAX to run the program, right? And back then, like in the year before year 2000, a lot of people still need to write the program in assembly, right? For optimization purposes. How many people remember those like game cartridges like Mario 3 that comes in a cartridge? Anyone remember those? Too old. Yes. So they actually the program. So those what so anyone have a cracked like anyone crack this thing open and see what's inside? Anyone try that before? Nostalgia. Even to myself, this is a really old thing. So if you crack it, oh well, true, because those things are expensive and you should not do that. But if you look at the inside of it, it's just a board with a bunch of chips. There's a chip that contain the program that is the actual game, right? And this thing has a really small memory. And what we establish, right, with the computer, you put a program in the memory, right? So let me ask you this. If I have limited memory, what do I have to do to fit a complex game inside those cartridges? What can I do? One thing I can do is I would optimize the assembly code so that I have fewer instructions. That this code is it's not an actual compression on the code, but you change the code itself, right? So that it becomes shorter. Or just make it 3 this long. Not sure if it is viable for the cartridges actually. I mean, I don't think I ever seen like a game with 3 different cartridges, but this, yes, disk, yes. The reason why I think this is working because they would have the module that will store the game's data, right? So you put in the disk, the disk get read, right? And then it actually just transfer the program's data to your machine, which is the game console, right? And this is more like a modern day console game, right? But back in the day, the actual code is actually on the cartridges. So I'm not sure how you would link the 3 parts of the same program onto 3 different characters unless you have 3 different like slots for it, right? So you can't do that. So you need to modify the assembly to fit the complex game into it, right? So if you like, for example, I think I've seen like old documentary about the like senior programmer from Nintendo, right? That were joking about like you were designing the game and then you had to think about, yeah, these are cool. I want to basically be able to display a complex character on the screen, right? But how do we do that? What optimization do we have to do to actually fit in these complex characters so my game is really complicated, right? And it's fun. So those are some of the things that assembly can do, right? But now let's come back to the content of our class. So I for historical reason, right? So if I have a game that works on an ISA, I need to keep the same assembly name, right? So that I don't have to reprogram. That's a lot of overhead. But now I have register, I have the data, right? I want to be able to move them around because my CPU can only access the register. To do that, because your data is in the memory, right? Data is in the memory. Data is in the memory. And your CPU can only access register, which means that there has to be an instruction that moves the data from the memory to the register. That's the move instruction for you. Move instruction can be used to move data from what we discussed last class, right, on Tuesday. It can be used to move from one place to another. So here's the format. Move like Q is a suffix that can be changed to B, byte, W, word, L. So basically, each of the suffix will move the bytes to the destination, right? Move source destination is as simple as that. I move the data from source to the destination. The operand that go into the source and destination can have multiple formats. It can be a constant integer, like move 10 into some location. Move a hex number to A, right? The source and the destination can be a register. Move whatever is inside the register, whatever value is stored there to that destination. It can be the memory and the register too. Move the data from this location to that location, or move from this location to the register, or move from the register to that location in the memory, right? So, for example, move Q would move 8 bytes, right? N, the consecutive bytes of memory starting from an address +1, +2, +3 until +7 if you use the command move Q. So we'll go through some examples to make it more concrete. For example, I can do move Q for Rtx, move Q for Rtx. What would happen after this? After I run this, what will be stored in Rtx? 4, yeah. This is the same as I say temp equal 4, right? This is the same as temp equal 4. If I want to use an address, I can have parentheses around that thing. So if I put parentheses around something, this becomes the address. So move -20 parentheses RAX is the same as I treat RAX as an address, and I move -20 into that address. So in the code in C, this is the same as *p, like some pointer represented by RAX equals -20. I can also move from one register to another. Move %R9, R10 means A equals B. I move whatever is in R9 into R10. I can also move from the data from R9 into whatever address R10 is pointing, right? This is the same as *A equals B. This what it does, what is this? So let's say R9 is 10, right? This means I'm gonna move whatever is inside the address. So this is my DRAM, right? This is address 10. And I have some value x in here. I want to then move x into R10. This is the same as A equals star B, right? So over here, there's multiple ways you can move data around. You can move from memory to memory. If the destination occupied, yes, it will get overwritten. It's as simple as that. If there's something in there, overwrite it. Assembly is simple. You just do whatever you're told to do. That's all. All right. Any other questions? So the next thing is you notice, right? I have a way to specify the address. So I have a different way I can specify the address. These are called addressing mode. This is the definition of how do I obtain the operand. You can do something like the absolute addressing mode, which is I get the value at address 10. I can do register indirect, get the value at address used by R1. Then I can do I start at R1 and then I add some offset, right? The value of R1 plus some number. Each ISA like ARM processor, Intel processor, what else? The MIPS processor used in PlayStation 1 and 2 will have the definition of how to write this. And you've seen the book, right? The manual that I show you, the one with 4,000 different pages. They will have the explanation of how does the addressing mode work for that ISA. But the question, the first question, right? Why? This allows you to save the number of bits that required for the address, right? Because if you have a 64-bit machine, your address is going to be 64-bit long, right? Are we all agree on that? In a 64-bit machine, my address is 64 bits long. So then if I want to represent an address in my instruction, how many bits do I need for that? At minimum. How big is my instruction? If my address is 64 bits long, I want to do something with my address, it's gonna be at minimum 64 bits, right? With some more, because you need to be able to say, hey, that's a load, that's a move instruction. So you need additional bits, but at minimum you need 64 bits. And that's too long, right? You don't always want that. So instead of using 64 bits for the address, I can just use a pointer, right? Whatever is in the register, that's your value. You can use that as the base and then add something. For example, how many people write a program this way? For I equals 0, I is less than 10, I plus plus, and you do something like I plus, I don't know, 10, right? Equal I. What is this? What is the base here and what is the moving value? I is moving, right? So you will first store 0 into A10. Then you store 1 into A11, right? This is basically A of 10 equals 0. A of 11 equals 1, blah, 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 right? Until A of 9 equals 9. So the base is 10. 10 is the base, it's fixed in there. And then the value I is the offset that you can keep adding, right? You can keep displacing from the base. So a format that is similar to this is going to be useful in assembly, right? Because you write a program this way a lot. So the people that design the ISA say, hey, we should have multiple ways we can use the address. The x86-64 say here is the addressing mode. there are 4 different numbers you can put in here. Notice the parentheses. So let's go one step by step, right? Let's go step by step. If you see parentheses, what is that? Again, what parentheses is used for in x86? Is that data or is that address? It's for the address, right? So every time you see parentheses, it means I'm looking at DRAM. I'm looking at the address. Inside the parentheses, there can be 3 different numbers. You can skip some of these numbers, it's fine. You can skip the number. You can have all the 3 numbers. Outside of the parentheses, there's 1 additional number. So I can have something like this. Every time I have $sign and it means a value, right? Every time I have $sign means it's a value. So I can have $10, RAX, and then RBX, and then 4. I can have an argument like this. What it really mean is this is the address at RAX plus RBX multiplied by 4 plus 10. So you start with RB, you add RI multiplied by S. So you have RB plus RI multiplied by S plus D. So your address is basically that. Right? Your address is RB plus RI multiplied by S plus D. Any question? Any question? So it's a formula. Usually we don't have to memorize a lot of things. Yeah, sure. So to specify the address, right? To specify the address, you can use parentheses. Inside parentheses, you can put in 3 numbers. You can put in 3 numbers. The first number, the second number, the third number. Outside parentheses, you can put in 1 more number. Your address is gonna equal to the first number, RB, plus the second number multiplied by the third number, RI multiplied by S, plus whatever is outside of the parentheses. All right. Whenever there's an R, it means it has to be a register. It has to be a register. All right. So it can be like EAX, EBX, 4. It means I'm gonna use EBX multiplied by 4, add that to EAX, and add some distance to it. And then that's my address. All right. So it's as simple as that. It seems complicated, but that's it. I can then use something like in parentheses %RAX. That means I just look at RAX and that's my address. That's also okay. All right. Yeah. D plus RB plus RI multiplied by S. Really simple. Looks confusing, but really simple. So let's do a swap function, right? Our friend swap X and Y. So this code, can someone tell me what does this code do? I have X and Y in as a pointer. All right. Yeah, it swapped the value, right? The value in the pointer would get swapped. So let's assume this. Let's assume X is in RDI, Y is in RSI, temp1 is in RX, temp2 is in RDX. How do I write this function with move Q? So basically move Q something. I can do move Q 4 times actually. And then I can swap the content. How do I do that? Again, let me do this. Source, destination. So let's look at the first line. What's the source? What is the source? the value at address X, right? The value at address X. So yes, X is RDI, right? X is RDI. But I don't want the value of X. I want the value at address X. So I need the address. So that's my source. What's the destination? What's temp1 here in the assumption? Temp1. What is the register? R A X, right? So we're done with the first line. How about the second line? What's the source? RSI, right? Destination is temp2. What's temp2? RDX, yes. Then what's next? Now I need to put temp2 back into dollars. No, not dollars. Sorry. Address X, pointer X. What's temp2? RDX, right? And then over here, %X is RDI, right? Over here, %RAX. Over here is %RSI. Now we just did a swap in assembly. All right, any question? Whenever you have parentheses, it means treat this as an address. So let's say the value of RSI is 20, you go to address 20, and that's your data. So whenever you see parentheses, that is an address. Think of it as a pointer, basically. All right, clear. I like, this is a great example because it shows a direct translation line by line. You can look at each line and you can write assembly code for that line. All right. So here's the actual implementation. If you look at the PDF of the slide, you see this as well. Yeah, so that's the solution. Now we have addressing mode, right? And sometimes we want to just compute the address. Sometimes, like, I just want to do star p, but I don't want the value. I just want what's the value of p. I just want the value of my address. So we don't use the move instruction for that because we don't move the address. We move the data from the address. In this case, you can use LEAQ instruction. LEAQ instruction. Source is the addressing mode expression in that thing. So that's your source. That's your source. It will be in this format. Destination, right, is the address denoted by the expression. So you got the address back. So the usage, there are two things that we use a lot here. The first thing is we can use it to translate the address. You compute the address without using a memory reference, right? So this is quick, basically. You can now get the address quickly. The other thing is in x86 in the GCC compiler, whenever you have argument in this format, x plus k multiplied by y, x plus k multiplied by y, sometimes compiler would cheat using LEAQ instruction. Why? Why is that possible? One thing I can do is to store x in RB, store s in k, and store y in Ri. Instead of running the multiply instruction followed by an add instruction. So this is basically, you first need to do multiply, right? Followed by an add. Two instruction, multiply is actually taking some time. It's long. If you can change it to just LEAQ, it's a lot faster. It's a lot faster. And you just put x in RB, y in Ri, and you just do this. LEAQ, right? B, R, I, S, and then destination. and you get the results. For example, I want to multiply by 12. I want to multiply by 12, right? I want to multiply by 12. What is 12? What is 12? X multiplied by 12 is basically 4 multiplied by 3x, right? 4 multiplied by 3x. Are we all with me so far? X multiplied by 12 is 4 multiplied by 3x. With shifting, what can we do? If we can compute 3x, what can I do with the result to get 12x? I can shift to the left by 2, right? Yes, left shift twice. That means this is basically 12x. So now, if I can somehow get 3x, I can get 12x really quickly. How do I do that? Let's say this is RDI. X is RDI. I can do this. LEAQ, RDI, RDI2. What is that? Can someone tell me, yes, it's x plus 2x, but why is this x plus 2x? Why is this x plus 2x? X. This is RDI, right? Plus 2 multiplied by RDI. And what is RDI? RDI is x, so this is x plus 2x. Now, RAX restore 3x. And then I just left shift RX by 2. I got the result. How many? Let's say I want to make you guess how long does it take to shift. How many cycle? Can you give me a rough guess for your guesstimate? Like how many CPU cycle would it take to do the shifting? 1. Most of the time it's 1 cycle. Why? You're just shifting in the wire. It's actually really cheap. Most of the time on a grand scale of things, this is 1 cycle. Oh, shift? You mean here? One to do all the shift. You want to shift by 12, 1 cycle as well. So can you explain the shifting again? You mean this? So for that, right? Let's say I have A shift left by B. This is equal to A multiplied by 2 to the B. So that's the trick that get used a lot. Like A left shift by B is A multiplied by 2 to the B. And shifting is cheap. Shifting is really cheap. So my point is shifting is cheap. Adding is also really cheap. On the grander scale of thing, add typically 1 cycle. Typically an add take 1 cycle. A multiply, that takes longer because multiply is a bunch of adds together, right? So over here, you just save maybe 50% of the time. Is that good? 2x speed up. Your program just now get double the speed because you don't have to do the multiply. And compiler do this for you. Isn't it nice? GCC, for example, would actually try to detect this and do it for you. So here's some. So are we all okay on this slide? Because the next slide I'll show you different instruction you can use. Oh yeah. So this is shift arithmetic to the left. Shift arithmetic to the left. So it's arithmetic shift to the left by some number. Yeah. So here are other instructions you can use. you have the add, subtract, multiply, shift left, shift right, AR, shift arithmetic to the left. Logical shift to the right, XOR, and or increment, decrement, negation, and not. These are some of the more common instructions. And here are the meaning. No need to memorize it. No, we'll give you the table. All right. We will give, it's open book. You can look at this table. No need to memorize this for exam at all. No need to, right? I am all for education where you don't have to memorize a lot of things. Anyone actually, I have a backstory. I used to like, hey, maybe I should go to med school, right? And then I hate remembering things. Yeah, I hate biology because it has to, like, I have to memorize a lot of things. Further in life, actually, it's surprising to me that biology is actually a lot about logical thinking. So you don't have to remember everything if you know how what's the scientific reason behind certain thing you were trying to memorize, right? But back in the day in high school, we basically memorized the heck out of biology, and I hate that. So I'm like, okay, maybe I should do math. And because I like playing games, so I was like, okay, maybe computer engineering is a good path for me. So I'm like, yeah, sure. And then for me, I am always don't like an education where you have to memorize a lot of things, especially when there's a reference material that you can look at. So no, you don't have to remember this. What's the difference between arithmetic and logical shift? Can someone tell me the difference between arithmetic and logical shift? Because we covered this already. So how about we take a break? How about we take a break? And I'm gonna wait until someone tell me what's the difference between logical shift and arithmetic shift. The name suggests the meaning, and one of them would keep the sign. Basically, one of them would keep the negative sign. So someone, yeah, biology is actually once you see like what's the proof, right? The scientific proof of certain behavior is actually a lot about logical reasoning to explain certain phenomenon in biology. But that's from my perspective as a computer scientist, right? So it's different. I'm not the biology expert. I guess I have to talk to my wife who did got a PhD in genetics. Um, yeah, like many things has building block that like fundamentally, I guess you can compare, right? That look similar. So let's take a 5 minutes break. We will resume at 3:05, right? And once we're back, someone need to tell me what's the difference between logical and arithmetic shift. Which one will keep the negative sign? Yes. Yes. As the name suggests, right? Arithmetic is a math operation. So if you do the shifting that way, you should keep the sign bit. Logical shift, because it's a logic operation, I don't care whether that's a positive or negative, so the sign is gone. All right. So that's not how I memorize it. Because arithmetic is number, logical is bits, right? So with bits, I don't care about the sign bit. So let's do a 5 minutes break, all right? We will be back at 3:05, and yeah, so you have already the explanation about difference between arithmetic shift and logical shift. So we resume at 3:05, all right? Let me pause the recording. All right, so let's resume the session. Actually, there's a great question down here. There's a question that asks, how do I tell what variable would be translated to Rtx or Ibx when you actually program? Let's say you program in C, right? Is that your question? Like, let's say I use Python, I use C, I use Java, and how do I know which one of the register would be storing each of the value I use inside the program? sorry, I want to make sure because this is a private question, so many of your friends will not see the question, but it's a great question. Are you back? Oh, am I gonna do assembly programming demo today? Nope, no, definitely no. So the question is, when I program in Java and C and Python, right? How do I know what register would take each value? So I just want to double check that's the question being asked. Okay, so that's the magic that happened during the compilation phase. So yes, depending on what the compiler choose to do, right? Because compiler has the task of changing, basically morphing your program's code in C, in Java, into assembly, right? So one of the tasks is called register mapping. It maps, right? It maps different register into different variable used in your program. How many people take algorithm yet? And anyone took algorithm? Okay, so I guess it's a little bit too early, but I can tell you that there's a certain algorithm, a certain graph algorithm called graph coloring that can be used to determine how many register that I need to store all the value and how do I process through my program with the register set that I have with IX down to R16, right? So these are done through the compiler. How can you tell which variable is what? That's when you need to look at the assembly code and then you will figure out, okay, this variable is for this register and the inverse. Basically, this register is storing this data from this line. Right? So hopefully that answer is more clear. Basically, compiler would translate the code from the language into assembly. And then inside there, it would map the register into the variable name. And then you will see, well, when you look through the assembly code, you'll see that, okay, that's temp1, that's variable X in my program. All right. So now let's continue on. The next thing that I need to talk about is there's also this thing called processor state. What is a processor state? These are some of the things that the programmer can see. For example, temp data, like things that are stored in the register. The programmer can see, the programmer can actually modify the assembly code and change the data. The location of runtime stack, the RSP, like the value of RSP, the current instruction, RIP, these are the program counter or instruction pointer. That's why it's called RIP. Instruction pointer. Or the status of the recent instruction. If there's a carry, if there's a result in a zero, yes. Or overflow or sign. Right? If it result in a negative number, the sign bit will be 1. If it's overflow, the overflow bit will be 1. If there's let's say you add 2 number and that's a carry, the carry bit will be 1. If you subtract 2 number and the result in a 0, the 0 bit will be 1, right? This condition code play a big role in a lot of programming tasks that modern program use. Whenever the carry bit is set, you know that you're adding 2 numbers, you ended up with some extra carry that's not representable by the results. You can check or compare the code if 2 values are equal by using a subtract, and you get to check the 0 bit, right? If 0 is 1, it means the 2 numbers are equal. The sign flag can be checked if you do something and result in negative number. Overflow flag is when the instruction overflow into the next bit, right? The difference between overflow is so the carry, right? When you add two number and carry, it means that there's something result in the bit that's supposed to go here, but you don't have the bit to store that. Overflow is when, for example, you go right from 1, 2, 3, 4, 5, and this is the basically the maximum. Overflow means your operation goes in here beyond the maximum or under the minimum, right? The negative minimum. So that means it's overflow. So all these flags are set implicitly on arithmetic instruction, except for the LEAQ instruction. Let's say I add the two numbers together and result in a carry. The carry flag by default will be set to 1, so that you can use conditional instruction would check the carry or the 0 flag later. You can also set this flag manually by using the compare instruction, like compare source 1 and source 2. Compare source 1 and source 2. This is basically as if you're doing if basically this is basically doing sorry, source 1 minus source 2, and then check the flag. So that's a compare operation. And you would set the flag based on these logic. So if source 1 and source 2 result in the carry out in the most significant bits, you get the carry flag to be 1. If source 1 equals to source 2, 0 flag is 1. If source 1 minus source 2 is less than 0, then sign flag will be 1, because when you do subtract, it's less than 0. Overflow is basically when you go over the maximum or under the minimum. So this is a little bit more complicated. It's going through the logic below, right? You can also, now that you set the flag, you can then test by doing test kill source 2, source 1. This would also explicitly set the condition code. This is the same as computing, not subtract, right? Compare would compute, compare would do source 1 minus source 2. Test will do source 1 and source 2. Without writing anything to the register, I just want to look at the flag. And the condition code in the register can also be set, right? I can set the condition code. For example, I want to set the 0 flag. I would set to set E. Set E would make it equal. The 0 flag would be 1. And these are the table. You can do set NS, set not sign, set sign, set not equal, set greater than. Set greater than means is sign flag, X or overflow flag. So these are, again, you have to look at the table, and once you see the instruction, you can follow what the table is actually doing. And note about the set instruction, only set the lowest byte of the destination. So typically you would pair that with move 0. Basically make sure every byte except for the last byte to 0. So to set upper 32 bits value to 0. For example, if I want to check and return if x is greater than y or not, so there's a C code, right? You can do compare. Then once you compare, you set if is equal, right? Then move the rest of the bytes to 0. Now we are done with condition code. We are done with the most arithmetic operation. The next thing we have to talk about is the program counter or the instruction pointer. This is how you move through the program. This points to the next instruction that follow after current. Is EAX a typo? Here? You mean here? No, actually, because this is a 32-bit instruction. EAX is also 32-bit. If I want to use the 64-bit version, I need to use a different command, and then I can use RAX to take it. So the instruction pointer, the pointer to the next instruction that follow after the current line. This is used to alter the flow of the instruction. So what code in C would alter the flow of instruction? What are the command in C code that would allow me to jump through a bunch of code block that will prevent me from if else? Yes, thank you. Things like if else or for loop. Why is for loop also jumping? Can someone tell me if what happened to the for loop? When you go back to the beginning, it's iterating, right? So at the end, you don't go to the next line, you go back to the beginning of the loop. So that means you're jumping as well. These are useful to implement if, else, and loop, and it can be modified using the control instruction. For example, you have the jump instruction, jump there. Basically, jump to this address. And that is the address of the code you want to jump to. We can do jump to address 20, would jump to line at the address 20 and keep running. And jump will check the condition code, because if you just do JMP, that's always true, you always jump. JE means that jump if the previous instruction result in an equal, like you compare, for example, compare source 1, source 2, and you jump E. You can do like compare, right? Compare source 1, source 2. And then you do jump E, jump if source 1 equals source 2. J and E would jump if source 1 is not equal to source 2. JGE, for example, here, jump if source 1 is greater than or equal to source 2. So you can use jump in conjunction with compare, right? So that you can do if-else statement. For example, right? For example, if I want to do if x is greater or equal to y, right? Do something else, do something else. I can then do compare x greater or equal to y, then jump to here. Otherwise, you go to the next line. All right. This jump, think of it as this is similar to the go-to command. This is the command that I don't want you to use in C code, but it's a command that exists. It allows you to jump to the line in C code that you want to go to, and please don't use it in C. It can result in some like some weird behavior. But think of the jump command like the go-to command in C. And this can be used to implement a loop and also implement an if-else. These are the jump command. All right. The next command is the conditional move. Conditional move. This is the same as the move instruction, but it looks at the condition. It looks at the condition. For example, conditional move if less than move is less than. So it's condition depending on the condition of the previous instruction, which is this guy. You either move Rtx to Rax or skip that line. This is a limited form of the predicated execution, so you will not see this terminology in, I think, in anywhere except if you take com art class on your 4th or 3rd year. Then that's a special topic class. We don't open that every semester, and try and still open it basically we talk about how to design a computer, but it's a form of a technique we call predicated execution. You run the code only if things becomes true. If the condition is true, you run the code, and it allows a lot of compiler optimization with predicated execution. So we're gonna skip the benefit. It's too advanced, and I don't want to cover that. But the gist of it is, don't use conditional move if your if else is big, because you are doing both part, right? Conditional move should be used when you just do something quick, like if a equals b, a plus plus else b plus plus. Like this is actually fine with conditional move. It's only one instruction. But if the if block is huge and the else block is huge, don't use conditional move for that. It's actually inefficient. So that's the end of the compute instruction. And also the memory instruction. So what are the memory instructions that we just covered? How can I move from, how do I move one data from one place to another? What command do I use for? Just to recap. What command? The first command is, yes, move Q. Yes, thank you. And for the compute, is add, subtract, compare, conditional, also conditional move, right? Not compare, test, right? The LEAQ, the one that computes the address. So these are the compute instructions. You're doing some computation, right? And again, now let's look at how do we implement a loop. How do we implement the loop? And we'll go with our example, right? We'll go with our example that use the jump instructions. And here's the example. Here's the example. Let's first look at the code in C. What does the code do? Can someone tell me? So let's look at this for maybe 4 minutes and see what does the code actually do. This is actually almost similar to your in-class exercise from Tuesday, but it's doing something a little bit different. So if you still need to implement your in-class exercise, look at this code, modify a few things, and you get the parity bit. But this one is not calculating the parity bit, it's calculating something else. What does it do? So let's say x is 5, right? So what's 5 in binary? What's 5 in binary? Yeah, it counts the number ones of the input x in the binary format. So if x is 5, which is 101, pop count will return 2. If x is, what should I do? 15, right? What's 15? 15 is 1111 in binary, right? So pop count will be 4. Count the number of bits that are 1 inside the number x, represented in the binary format, right? So hint for your in-class exercise, you can modify this code here to get the parity bit. You're not summing, you're doing something else. But the C code can be translated from a loop, right? Do while loop. So that's a loop right here. You see the loop, right? You loop until x becomes 0. You loop until x becomes 0. So I can change this loop to use goto by first have a label, right? This is the label. And then you go to label. So if x is still non-zero, go back to the beginning of the loop. Any questions so far on why the goto version? Let me pause for 2 minutes so that you can look at the code. All right. Now that we're back from the quick 2 minutes break. Yes, go to work with label, go to work with line number. But here's the go-to version. So let's use jump and conditional code to do the code here, to basically to implement the do while, right? This is a function set. So I'll call different portion of your code like this. Function setup. Function setup. This is your loop. And this is your condition, right? And this is your return value. All right. Now, if you look at the loop portion, what does the loop do? What are the main operations in there? Can someone tell me what are the main operations that you have to do? There's an and, right? What else? What else are in there? The add, right? You add, you shift, and you have the if else, right? If x, basically what is if x? What does if x really mean? This is basically means if x equals 0, right? Check if x is not 0. All right, are you all with me? Basically, if x is the same as if x is not 0. Right, with me? Anyone lost here? If x is the same as, I check the value of x and it's true. Yeah, if x is non-zero, that's true. If x is non-zero, it's true. A better format is this, actually. Sorry, it was dumb for me to write this. If x not equal to 0, that's a much better form. Yeah, sorry. It's the same thing, but this is much better to understand. So let's go through the assembly line by line. Let's go through the assembly line by line. What we need to assume first, in assembly code, in x86 assembly, one thing you can always assume is the return value will be in Rtx. This is the assumption. Return value at the end of your function call will be stored in Rtx. Depending on the version of your chip and the compiler, the arguments can take different register value. But let's assume x, which is our input, is in RDI. So what's the first thing we do? What's the first line in my function? Here, right? What does that line do? Set the value of result, which is Rtx, right, to 0. It's this line right here. We set result to be 0. So what do we do next? You set a loop, right? So you label the loop, right? And then, right, to be honest, the next line, because the input is in RDI, and I need to modify our input because I need to shift, right? I need to shift afterward. So one thing I do here is put RDI into RDX. So right now RDX is gonna equal to X, right? Our input X in percent RDX. Then I AND 1 with EDX. What is EDX? Can someone tell me what's the difference between RDX and EDX right here? What's the key difference? Which one is 8 bytes and which one is 4 bytes? RDX is 8 bytes, EDX is 4 bytes, right? And we know that if we AND something with 1, I don't even need 4 bytes, I just need the last byte, to be honest. So it's okay to use EDX, right? So in the process of pipeline, this can actually make a small difference, can be a little bit faster. So what you do here is temp equal to x and 1. Basically, you're doing this part level number 1, right? This is number 1 right here. You then add what? You add Rtx, which is the result here, add results equal to t plus results. So you're doing this step 2. The next thing is you do step 3, right? On your code here, shift right by 1, shift right RDI by 1, step 3. Then what? If x is 0, after you shift, if x is not 0, what do you go? Where do you go to? If x is not 0, go to L2, right? So that's a great question. The question is, what's the, like, for say RAX and EAX, right? They take 4 bytes. One of them take 4 bytes, one of them take 8 bytes. But are they occupying the same location? Yes. Yes. Let me find an. So if I go back, right, I just want to find a space. So let me find a blank slide here. Sorry, I'm gonna jump around a little bit. So I'm gonna use this. No, I thought I have room. So let me use the room here. Okay. This is, let's say this is RAX. Let's say this is RAX. And let's say my value, give me some random number. Give me some random number. All right, 64,209. So we can have 64,209. All right. I don't want to convert that to binary, but I think this is, how many bytes is this? How many bytes is this? So how many people think this is actually greater than 16 bytes? I can tell you that 2 to the 10 is 1024, right? And then 2 to the 6 is 64. So if I have 2 to the 6 multiplied by 2 to the 10, that's 2 to the 16. That's 16 bytes. That's 64 multiplied by 1024. My question is that bigger than 64,209 or less than 64,209? It should be bigger, right? I multiply 64 by 1000, I get, so this is multiplied by 1000 plus 24. So I get 64,000, right, plus 64 multiplied by 24. I do 60 multiplied by 2. Wait, that's close, actually. No, not close at all. Yeah, actually 64 multiplied by 24 is way bigger than 209. So how many bytes is this? Is it bigger than 16 bytes or 16 bits? My mind. Is it bigger than 16 bits or lower than 16 bits? So 64,209 will fit within the 16 bits. All right, you fit it in the 16 bits. Now, let's say I do move chill $ 64,209 percent RAX. This is what happened. I put 64,209 in the RAX, right? So what goes into the rest of my bits here after bit number 15? What is the value in there? I store 64,209 in here. What's in there? How do I represent 64,209? What's the value in there? These are all 0, right? So now Rax is going to equal to 64,209. EAX means that I'm going to change the ink color a little bit. So EAX, I would take this part. So EAX is going to equal to, again, 64,209, right? What's the next jump? The AX, right? Percent AX is going to equal to what? Percent AX, again, let me use a different ink color. Percent AX, I'm going to take the first 16 bits. So that's, again, this will be 64,209 because it's within 16 bits. Then if I do percent AL, right, I would just take this part, which is some number that's not 64,209. All right. Is it more clear? Basically, they occupy the same location, but when I said RAX, I take all the 8 bytes out of the 64 bits. When I said EAX, I only take the first four bytes. When I said AX, I take only the first 2 bytes. And if it's AL, only the last byte from bit 0 to bit 7. Now, is it more clear? Yes, no. If it's a long pause like this, I cannot tell if it's more clear or less clear. So you need to lead me in a little bit. Yeah, it's just the AX of the different sizes. Yes. Yes. And for RAX, for example, you can put in a number that's really big, right? It can go to the 6 bytes, the 7 bytes, and that's okay. If you know your number is big. If you know your number is not that big, you can use EAX. You can even use AX as well, right? Now, where were we? Yeah, here. All right. So we're almost done with our go-to version, right? If X go to loop. So if the shift doesn't result in a 0, you loop around. So jump not equal, you go to L2. And that's it, right? So in general, the do while would be converted like this. So you have a do followed by a loop body, right? You would then convert to a go-to version by first label the loop, write the loop body. If something happened, like the same condition here, go to loop, right? Then you would convert this to assembly. Again, you would do the loop label, right? Your loop body goes here. And then you would do the jump depending on the condition. Back to loop. Then you can say, I want to implement a while loop, right? So the while loop is a jump to the middle translation, to be honest, and you can actually see this if you add the dash OG in the GCC command. Dash OG is optimized debugging experience because it will prevent crazy optimization from your C code to assembly, and it allows you to see more of a direct translation of your code. But you can do this while test, right? It would convert to first, because while loop, you first run the loop, right, before you test. No, sorry, you first test before you my bad. While loop, you test, then you do the loop body. So the first thing is you go to test, jump to the middle, right? Go to test. If test is true, then you go to the loop body. So you first do the test. If false, you finish. So you can convert the same program. This is the same program. You can convert this to the jump to the middle format. Again, go to test. You first do the condition check. This looks the same as our do while example, right? So initially just jump to the test and then test go back to the loop, and that's all. The only difference is you first jump to the test, all right? And now you have the way to implement the while loop. And you can convert while to a do while by, instead of -OT, you go -O1. -O1 will enable the optimization where the while loop would first get converted to this format. Can someone tell me why is this a little bit better? Better than our earlier example. This is a little bit better. So let me go back to an earlier example again, right, to show you the difference. So here you go to test. You go to test. By default, you always go to test. If test is true, you go to loop and you loop it back. Now, with a small optimization, with a really small optimization, what's the difference? Can someone tell me what's the difference? Well, if you just test it first, you can skip to done, right? This is basically allowing you to skip the case where you don't enter the loop. So it's a little bit better. You don't have to even go and check the loop body if it's not true in the first place. You don't jump a few more times. So we can change this again. If not X, go to done, then you loop. Then here's the loop body. Similar to our do while. And the initial condition, the not X, will prevent you from going into the loop. All right. Now, what's the one type of loop I haven't talked about yet? The last type of the loop that we use a lot, actually. So we have the do while, we have the while loop. Now you have the for loop. So for loop is actually really simple, to be honest, right? For loop generic form is init, test, update. What are the two things from here, init, test, and update, that we have to do only? Well, what's the one thing here we have to do only once? And what's the one thing that we have to do at the end? So init, we do it only once, right? Then you finish the loop with the update. Then the rest are the loop body. All right. So we can do p count using the for loop again. We are not going to go through the example. Hopefully that's clear. We count the number of ones bits, right? But we will show the conversion from the for loop to the while loop. What's the conversion? To be honest, is really simple, right? You first init, the rest test, update, and that's it. Now you have the while loop. All right. And with the while loop means that we can change to the do while loop through the earlier example, which means we can now change to the go to example, which means now we can change to assembly, right? And here's the example. Now we just switch from the for loop init, right? Init. Then this is the test. This is the update. over here, and here is the loop body, right? And then with this, you can switch to a go-to version by, again, init test go-to, right? Go-to done if it doesn't become true. Then you do the update at the end, you test, and you go back to the loop body, right? And if you know I in the first place right here, do you have to do the first test? If I is 0 and you know W size is not 0, someone tell me, if I know the value of I mean by default I know the value of I right here. Do I have to do this part? Is that part always true? Okay, so my question is, does this part always true or false? Do we go to loop or do we go to done? Always. With the for loop implementation, do we go to our loop or are we done? It always go to the loop, right? Because I is 0. W size is not 0, so it always go to my loop. So compiler would apply the technique, actually it's called constant propagation. What it really means is, oh, sorry. Yes, so I'm gonna finish up soon. So constant propagation would basically apply the constant value to all the variable that we know is constant to get rid of some statement. So this is done in the compiler. And that's actually it. So here's a summary about the control instruction, right? So you have if then else, which we can use jump for, do while, the while loop, and for. These things change to conditional jump, conditional move. Next lecture, we will talk about switch case and how do we implement it next week. All right, so that's it for the lecture today. Thank you so much for being here. I'm going to be here for maybe 3 or 4 more minutes for any Q&A. If you have to go to the next class, please feel free to do so now. And that's all. Yes, definitely. Yes. Thank you for the reminder. I will put that on my calendar. Thank you so much. Let me put that on my calendar right now. No in class for today. Just go finish up the one from Tuesday. All right. Yeah, this lecture is long because it's a bunch of new instructions. Upload lecture video. Okay, thank you so much. Yes, I'll post the video as soon as possible. So the in class we need to handle native integer. The input can be negative integer, but the way you compute the parity bits is the same. Count that 1 bit at the end as the 1 bit. I mean, think of it as if they are unsigned. All right. Treat the input as if they are unsigned.